Hi, welcome back. We're talking about using the RC circuit as a low-pass filter. And I'll remind you again that you don't need to know circuit analysis for our course Signals and Systems. So I redrew the RC circuit over here, and remember that the voltage across the series combination we're calling the input as X of t, and the voltage across the capacitor is Y of t, and I've also noted that the current through this series connection is I. Now if you perform Kirchhoff's Kirchhoff's voltage law around the loop, then you get that the source voltage X of t equals the voltage drop across the resistor, I times R, plus the voltage drop across the capacitor, which is Y. And the current through the capacitor, if you remember from circuit analysis, is C dV dt, or in this case, C dy dt, where the voltage across the capacitor is what matters in that equation. And that current is the same that current that goes through R. So we can replace the current I by C dy dt, and we get the voltage drop across the resistor is RC dy dt, and then the voltage drop across the capacitor is Y of t. Hence we have a first order differential equation, X of t equals RC dy dt plus Y of t. Now, we're going to program a filter. So when you get a software suite like some application that's controlling your headphones or something like that, or iTunes or Spotify has an equalizer, what you're getting is a package, a suite of programming. Somebody has programmed these filters for you already, so I'm going to show you what's happening behind the scenes there. Now, it has to be discretized, which is the conversion of continuous time to discrete time, and the way you do that is through sampling. And if you don't catch all of the sampling details here, that's okay, because sampling is a little bit out of the scope of our course. Anyway, we're going to change the t's to n's. This is part of the discretization process. So we have x of n is r times c. Now a derivative in discrete time does not make sense, and we've been saying for a while now that a derivative is like a first difference. So I'm going to write the first difference here. That's part of the discretization process. So my equivalent discrete time system looks like this. And I can solve this for y. So I get y of n equals x of n plus rc y of n minus 1 over 1 plus rc. Now I'm going to call parameter alpha to be 1 plus RC just for convenience, and then, and I'll let you verify this on your own, I can write this difference equation as alpha times xn plus 1 minus alpha times y of n minus 1 equals y of n. So here's our difference equation, right? I'll let you verify that that's true, but this difference equation is the discrete equivalent of our RC circuit. That's pretty cool in itself. Now, for my simulation, I'm going to choose that RC, the product of the resistance times the capacitance, is 33 times 10 to the minus third seconds. But, and here's the sampling part that you don't need to know, the program's going to assume that the time step is 1 second. And 1 second is too fast to see anything happen here, right? Or I guess our time constant is too fast to see anything happen if the sampling is 1 second, right? And so what we're going to do is we're going to sample this thing at 1 kilohertz. 1,000 hertz is going to be our sampling frequency. So this is 1,000 hertz or 1,000 samples per second. And again, you do not need to know anything about that. And all you should know is that we're going to replace RC with our sampling frequency times RC. Okay, and alpha is going to be replaced by alpha equals 1 over 1 plus Fs times RC. Again, you don't need to know why that is. Okay, so I'm going to take you through the process here in the code. First of all, I've got my time, and I'm going to make a plot of a lot of different things, actually, from minus 10 to 500. And x is going to be an impulse, so I'm going to set that to zeros, 10 zeros corresponding to minus 10, minus 9, minus 8, and so forth, and then a 1 at the origin, and then 500 zeros. There's my sampling frequency, 1000. RC is 33 times 10 to the minus third. And then here's my impulse response. I'm going to calculate this impulse response, and I'm setting it equal to 0 to assume a causal system. We don't want the impulse we don't want a response to the impulse before we actually put in the impulse. So the system is initially at rest. Now here's the alpha parameter, and then I'm going to solve the difference equation. We've looked at this before, so we're just going to iterate through updating the impulse response so that when this loop is finished, h of n is containing the impulse. I'm going to plot the impulse and the impulse response. Excuse me, h of n was containing the impulse response when that loop is done. So I'm going to plot the impulse and the impulse response. And I'm also going to look at the step and the step response because that's something that we considered in the previous video. So here's a step, right? 10 zeros because my time starts at negative 10, and then a 1 at the origin, and then 500 ones. That's a unit step. And then the step response, S, now that I have the impulse response, to get the output for any input, I just convolve, in this case, the unit step with the impulse response, and that gives me the response to the step. And so then I'll plot those things as well. Next, I'm going to show you, one of the uses of this circuit, and that is, for example, to filter out unwanted frequencies like received from an antenna. So here, I'm going to generate a fast and a slow oscillation. So x1 is a 1000 hertz signal, and x2 is a 100 hertz signal. And the idea is that our antenna, we're going to simulate an antenna, is going to receive both of those things. And we're going to try to remove the high frequency and just keep the low frequency of 100 hertz. Perfect for a low pass filter. So I'm going to make some waveforms here. So here's our filtered, or here's our unfiltered signal. So we receive x1 plus x2, which is the sum of the two waveforms. And then how do we filter it out? Well, then we take that received waveform x3 and we convolve it with the impulse response. That's sending it through the RC circuit, right? But just in a program. And then I'll plot that to show you what that does. Finally, I'm going to filter some audio so you can hear how audio is affected. I'm going to read in a clip, just a short, 5 or 6 second clip, and it's a stereo clip, so I'm going to separate the left and the right channels, and we're going to take a look at the left and the right channels, and then I'm going to send separately the left channel through the filter. So I'm going to convolve the left channel with the impulse response, and that makes the output left channel. And then I'm going to convolve the input right channel with the impulse response, and that makes the output right channel. We're going to look at those, and then I'm going to bring them back together in stereo, the Y's, the output, and we're going to listen to Y. We're going to write that to a clip, and we're going to listen to it. And then I have another demonstration, but we'll get to that in a second. All right, so let me hit run. Okay. One second. Okay, so I hit run, and this is the first thing to come up. So I've got here is my impulse, right? So you'll see that the blue, anyway, is the impulse. It's 0, then it's 1, and then it goes back to 0, and then the red is the impulse response. And we said that in a previous video, the impulse response was given by h of t was 1 over rc e to the minus t over rc times the unit step, right? And so that's the impulse response that you see there. It's 0, and then it shoots up real quick and then decays back to 0. So there's our decaying exponential. Okay, now in this window, the blue is the input, so that's the step. So that's like the switching in of a signal, a 1-volt signal, and then the red is the output, so that's the step response. So that's the capacitor charging up. Again, this goes in accordingly with the previous video, right? All right, so let me continue on. Okay, so here is a plot of our two waveforms. So these are the two signals. We're gonna sum them up and then try to filter one from the other. So you see a red waveform is a slow waveform. That's the 100 hertz signal. And then the blue waveform is the quick waveform. That's 1000 hertz. So that one oscillates 10 times as quick, or 10 cycles per one cycle of the red. Okay. Now our next, if I run the program, our next signal, this is the sum of those two quick signal, or those two sinusoids. So there's the slow one, the 100 hertz one is the kind of this oscillation. If you follow my mouse cursor, that's the slow 100 hertz signal. And then on top of that, superimposed on that, is this quick one. If you follow my mouse here, that's the quick one. So this is what you might receive from an antenna, and we're trying to get the slow one. So we're trying to remove that high frequency by sending it through our filter. So let's do that. Okay, so this is the output of the circuit, or the filter. So you'll see, first of all, that it has not removed completely the high frequency. So you still see these little bumps, okay? And that's just because the RC circuit is not a perfect low-pass filter. But it did do a good job, though. Those little bumps are just that. They're little oscillations, not like above it, where we have these large oscillations. Okay, so you should notice that, first of all. So the filter worked in filtering out the 1000 hertz signal. Also, notice the amplitude has gone down. And the reason the amplitude has gone down is that so our low-pass filter looked like this, and this was 1. So even the 100 hertz signal is getting attenuated by something, right? It's just that it's getting attenuated a lot less than the 1000 hertz. So if this is 1K, this is 100. So the 100 might have a factor of 0.8 or something like that. Don't take my word for that, though. And then the 1000 hertz signal might have a much lower factor, like 0.1. Don't take my word for that either. But the idea is that the 1000 hertz signal is getting attenuated more than the 100 hertz signal, but both of them are being attenuated, hence the decrease in amplitude here, 0.4 versus 2. Also, if you notice, there's a shift in phase even in the received signal, or the output. You see this signal, the input signal, went up first, and then it came down, and then it goes up, then it comes down. This one goes down first, and then it goes up. And the reason for that is the phase. So this was the magnitude response that I drew here. The phase response of the RC circuit introduces some phase difference. So here's the 100 hertz signal. So there's going to be a lag at 100 hertz. So yes, even the 100 hertz gets a little bit of phase distortion. So that may or may not impact your system. But anyway, we have that as well. So now let's continue on with the demo. Okay, the next figure I have here for you is not really informative, but especially like that. But this is the audio now. I'm going to read in an audio signal, and this is the top one is the left signal, and the bottom one is the right signal. And the reason I'm just showing you this is just to make the point that this is what a real discrete time signal looks like. One that is a real signal. I mean, we draw these little dots here and there. These very simple circuits or signals for homework and examples, but this is what a real application looks like. So remember, audio is sampled at 44.1 kilohertz. So that means for this audio signal, there's 44,100 points per second, and this might be a 6-second clip, so you can do the math there. So that's what we're dealing with here. And I'm just going to push enter again, and we get another plot, and this one's not too informative, but this is the output. So again, this is just to point out, look at all of these samples that we're dealing with, and again, this is the left output and this is the right output. And I'm going to hit enter again, and I think the demo is over. Now what I'm going to do is play the filtered audio clip for you. So just a warning, you might want to turn down your volume on your computer just a little bit, and if you have some good headphones, you'll want to use some good headphones right now. But I'm going to play the filtered and the unfiltered here. So this is the unfiltered, so this is the original. Okay, so that was actually studio produced. So, it's not going to sound better now that it's filtered. It's actually going to sound worse because that was the best it could sound. Here's the filtered version. Notice what you hear. Okay, so first of all, one thing that you might have noticed is that the filtered signal has less volume than the unfiltered signal, and that's again due to this point here, that all of the frequencies get scaled by something less than 1. So all of the frequencies are losing some energy, which means that the overall volume is less. But you may also have noticed that the second one, the filtered signal, sounds a little bit more bassier, right? And it sounds muddier. And that's exactly the point of the low-pass filter, that it passes those low bassy frequencies through, and it attenuates the high treble frequencies. Okay, now let me comment all this out and uncomment this part out. All right, now I want to give you another example. And it's not an RC filter anymore. I want to show you a different filter. It's a differentiating filter. This is a common filter. It's useful, and it has the input-output relationship that the output is the time derivative of the input in continuous time. Now, for software, well, actually, before we get to the discretization, let's try to figure out what the frequency response of such a system is. And if I put in ak e to the j omega 0 t in for x of t, right? What do we get out? Well, the derivative of this is j omega, actually, let's just drop the omega 0. Then the output is j omega times ak e to the j omega t, right? And so, of course, I get back what I started with. That's the idea behind a linear time-invariant system. And this thing that's multiplying it, this is the frequency response. So hopefully you understand that by now. Okay, that's the frequency response. So what does the magnitude response look like? The magnitude response of this differentiator, then if I take the absolute value or the magnitude of this, well, that's just omega, right? That's the absolute value of omega. And if I look at the phase response, so what's the phase of this thing? Well, if omega is positive, then I have a positive j, which is 90 degrees. And if omega is negative, then I have a negative j, which is negative 90 degrees. So that's the phase response for this guy. So that's a differentiator, and we can discretize it with, of course, there's no derivative in discrete time. We take the first derivative, first difference. So that's our differentiator in discrete time. It's a first difference. Now, how would this be useful? Well, one use for this thing is with images, and it's used for edge detection. So in an image, if you have an edge in an image, then that corresponds to a high frequency. Think about it. If something changes from white to black, for example, then that's a quick change, right? Quick change over a couple pixels. It goes from white to black. So that corresponds to a high frequency. So that high frequency gets amplified by quite a bit, right? But the low frequencies, like something that's not an edge, that gets attenuated. And so if we send an image through this first difference, or this differentiator, then we might be able to detect edges. So that's the demo that I have here. Let me run it. Okay, so this is the original image, right? So we've got some coins there and a black background. And let me push enter. And we get the output of the edge detector is this, right? So you see it has done a fine job detecting those edges. So I'll just say a little bit about the code. We're using a built-in image into MatLab coins, and it converted it to a gray image and just showed you the image, and then I send it to this edge detector, and the edge detector is doing exactly what we did in the first part of this. It's solving a difference equation. It's getting the impulse response of the difference equation, and then it's convolving the image with the impulse response. And I'm not showing you the gory details behind this function because an image is a two-dimensional signal. It has the x, it has the horizontal and the vertical, and so the convolution is actually two-dimensional convolution, which is a little bit out of the scope of the class. But it's doing what you would expect it to do, convolving the image with the impulse response, and then I showed you that filtered image. Awesome.